Hey, what's up? So, a few weeks ago where we left off in the part of the story is where the calcium is entering the muscle cell, all right? And remember, just to kind of recap, the bigger picture is discussing why it makes sense that the study that found that higher intensity exercise led to better control of blood glucose levels makes sense. So just kind of explaining the mechanisms and whatnot behind that to the best of my understanding. So like I said, where we left off was calcium entering the muscle cell, okay? So when calcium enters a muscle cell, a lot of different things can happen. We're going to focus on one aspect of that right now, okay? And that's the calcium is going to diffuse to where the actin and myosin are. So I'm a very poor artist, but I'm going to draw some illustrations that are in no way accurate, but hopefully help to get the point across. So if we're going to call this actin, I'm going to call this myosin. And that's the myosin head, okay? So when they're not bound, there's going to be, well, I shouldn't say when they're not bound, but there's going to be something called tropomyosin and troponin C, this troponin I, this whole troponin complex. They're kind of more or less blocking the myosin head from binding with the actin. Okay, it's covering the actin. So if we call this like tropomyosin, troponin C, troponin I, maybe something else, troponin, whatever. Okay, so that's not the point of this. The point is that myosin head is unable to bind to actin because there's this thing blocking it. Okay, the way to get this thing to move is when calcium enters the cell and it binds to troponin C. So if we call this one troponin C, it's going to change the charge distribution of this whole complex, okay? Calcium has 2+ charges. When it binds, it's going to change the charge distribution of this complex, all right? This is the complex of proteins. When the charge distribution on a complex of, when a charge distribution of proteins changes, it causes the proteins to shift their shape, all right? So, calcium binding to troponin C causes this whole complex to shift, which then allows the underlying actin to be exposed and the myosin head to bind, okay? So that's what we're looking at here. So I just removed it all, but that's what I'm trying to illustrate. This has shifted, exposing the underlying actin. The myosin head is now able to bind, okay? So, problem is it's going to remain bound until something happens. And that something is ATP has to break that bond. So, here we have, let's just draw it in right here. When ATP comes, ATP, and binds to the myosin head, again, this has a certain charge, protein will shift that shape, okay? Causing the myosin head to break free from the actin, kind of cock back. Or just rather break free. Okay? Now, on the myosin head is something called MATPase, all right? And what MATPase does is it breaks down ATP into ADP and one extra P. ADP plus P, okay? So again, now this is the different charge distribution, all right? ADP plus P is a different charge distribution than ATP. This is going to cause the myosin head to cock back. when this cocking back happens, P is going to leave. All right? Again, this changes the charge distribution. Which will cause the myosin head to then bind down. Because it's now shifted its shape again, it's going to bind to the actin, assuming calcium has come in and shifted the tropomyosin and troponin complex, okay, exposing the underlying actin. The shift of this is going to cause ADP to leave, okay? Again, this is going to change the charge distribution of the myosin head. And that will cause the myosin head to pull on the actin, okay? So we kind of have this process where it's bounding, ATP breaks the bind, and then based off the charge distribution, it's going to shift its shape, cock back, bind down, and then pull, okay? And so this is happening trillions of times, which is kind of everyday motion that we're seeing and whatnot, all right? So, the kicker, or the kind of big thing with all this, where we're leading to with this next step, is what happens to this ADP. Because there are a bunch of things that can happen, and that's what we'll get into for next time. So again, big focus is, why does higher intensity exercise seem to allow better blood glucose control than lower intensity, longer duration type exercise? Now we're going through all the mechanisms of why this has happened. Started with calcium entering the muscle cell, shifting the troponin and the troponin complex and the tropomyosin, exposing the underlying actin, everything that happens with ATP, ADP, M-ATPase, and now we're looking, okay, now we're bound, now we've pulled, we have this this ADP floating around. What's happening next? Stay tuned for that one.